Okay, so I wanted to start with something that is, I think, familiar to people. And so, of course, this is a little bit of a annoying, bad problem for this kind of session in the sense that I assume there are people here who will calculate this in 2 minutes. And then there are people who will take 2 hours. And then there are senior professors like me for whom it takes a day. And but so somehow, if many of you somehow feel that, so I really wanted to go through the Dirac algebra, which is kind of something that you exercise a lot. So we will. I think I will. How long does it take? Let's say 10 minutes, 15 minutes. Work on it, and we'll see how far it gets. Then I will ask somebody. Do it in 10 minutes. Just a very simple Feynman diagram calculation, kind of the easiest type of, basically the easiest, almost the easiest one that you can think of. Not yet. Just do it the way you learn it in textbooks. And then, of course, by comparison, we'll see how easy it is to do the other way. So here it's so these are the Mandelstam variables, which I assume you remember what they are. If not, ask me or ask a friend or Google them or something like this. So just don't let me interrupt. Just keep on working, and I will write something on the blackboard little by little. But just I don't want to interrupt your discussion. Okay, I see some people are still busily calculating, but did you... How many got this far? Good, good. A big crowd. So I think... so the ones who did not, let me first ask, is there something that you want to ask now? What, how does, about the calculation, how does, some technicality, why is there a 4? Ask questions? If not, then I will just say a few words. So as I said, this is something that if you practice this a lot, you do this in 2 minutes. If not, in a week, is you easily spend a week. One of the ways that with a little bit more experience, or with a little bit experience, which some of you probably have and some of you don't, you can look at this diagram and you can directly write down this expression. How many of you did that? Well, the way, or let me say, well, if you have enough experience, you can just look at this diagram and write down this expression. Of course, what they tell, the way where it comes from is that okay, you have to follow the fermion line. So you take u bar gamma mu u for this line, u bar gamma mu u for this line, then you square, and so then in the square kind of you see that this is a scalar. So u bar something u. And so the square of the amplitude decomposes into the absolute value square of this part times the absolute value square of this part. One of them is this one, the other one is this one. So there's two u bar gamma u bar gamma u, which are a square. And then the usual thing, you take this u and pull it over here. And then it's a trace. P2 gamma mu, K2 gamma mu, and then this was already gone because it was here. So a trace. One way to think of this is that, one way to somehow think of it is that you can actually, I don't know if you're used to this, but you can draw a diagram directly for the square. It can be useful to read it off. So what you can do is that you can take this diagram like this. Then you can say, okay, now let me draw the diagram for the complex conjugate amplitude on the other side. So if this is K1, the complex conjugate amplitude is just going to have a K1 that is continuing here. And this one is a K2. There's a K2 that is continuing here. They're going to exchange a photon. And now then, also it have to be the same. This is, for example, P2, and this one also has to be P2. So you can kind of draw this, connect this fermion line here, because this is actually the same thing as this. And this thing as this. So now you see that you have a diagram with a fermion loop. And then the way you read this is, okay, fermion loop is a trace. So this is a fermion loop. If this is, for example, mu, this is nu, you read that the fermion loop is K. There's a gamma mu. There's a gamma. Correctly read fermion loop equals trace. Follow the fermion loop. In what order do they go? K1 mu P2. No, so this is P1, of course, and this is P2. Like this. So you can draw a diagram for the square. Then when you connect these, you get a fermion loop. The fermion loop becomes a trace. Yes. Yeah. Yeah.
Now in the next time, why you are writing mu there?
So the question was, just repeating, I'm repeating for the microphone for the recording. So the question was, why, if there's a mu here, why is there a nu here? Yeah, so because in the amplitude, so in the amplitude, I'm summing over mu, right? So in the amplitude, there's a maybe I should have used another letter. Let me call this G mu prime, right? So I'm in the amplitude, I'm already summing over this index. And so in order to not get messed up with my indices, so this mu is mu and this is mu, and I'm summing over this index. Right. Well, I am writing G mu nu. Well, I was sorry, I was not very consistent. So let me write it like this. So the photon propagator is G mu prime. Index here is mu, index here is mu prime, right? And then, and I'm already using this photon propagator by writing this as gamma mu, right? Then propagator in the, so here this was a mu, so this was a mu prime with a G mu prime. There's other photon propagator in the conjugate amplitude, which is nu prime, and then the photon propagator is nu prime, right? So the index is different in the amplitude and the complex conjugate, and this is why I get this is why I get things like I have a trace. There's these two indices. So this and this and this come from the propagator in the amplitude. This and this come from the propagator in the conjugate amplitude, right? And because kind of the trace always the trace corresponds to this fermion loop. So the trace gets apart from the amplitude and the conjugate amplitude, and the other trace gets parts from the amplitude from the conjugate amplitude. And the propagator connects these two loops. So the propagator the propagator connects the two traces. There's the same mu appearing inside both traces because that's the way it goes. So somehow, if you do this a lot, which I don't, but some people do, you just look at this diagram, you think in your head about this kind of a diagram, and then you okay. What else? So the t squared, there's a t squared from the propagator. This 4 comes from the fact that I'm averaging over the incoming spins. And so the traces, yes, and the traces come from summing or averaging over the summing over. So that the relation is that sum over spins of u bar, so u bar of p of the same spin. So this has momentum same spin. This is p slash minus. So this relation is what turns these u into these slashes inside the trace. And so this expression at this, so notice here this is m dagger m, this is m dagger m's bar. So here I have summed over the spins and then put a 1/4 in front because I want to average over the incoming spins and sum over the outgoing spins. Good. Huh? Excuse me? Absolutely. Yeah, but my m is 0 now. Yeah, yeah. Sorry. Of course. Good. So this is how I got here. 1/4. So far the only numerical factor is this 4 here. From the fact that I want to average over incoming spins, then I have traces. Using this trace, so there's a 4 from the trace. I have 2 traces, so I have 4 squared. and 4 downstairs. So this is the overall factor 4. Then I look at the dot products with these p's and k's and identify them in terms of the Mandelstams. So note here everything is massless. So every dot product between two vectors is some Mandelstam up to some with a plus or minus and a factor 2 because here so a dot is Mandelstam divided by 2 and plus or minus depending on which one it is. So this is why I get S over 2's minus T over 2's minus U over 2's from this. So 3 terms, altogether 9 terms. Note that one of the terms has a coefficient 4, which comes from the G mu nu, so that gives you a 4. And the term with the coefficient 4 is a minus t term, so there's one with a plus 4 because this is a plus because it comes from the minus times minus. Then there's other terms which always come from a minus and a plus, minus and a plus, minus and a plus. So 1, 2, 3, 4 other terms, so all the terms proportional to t squared cancel. And what I'm left with is 2 terms with s squared. So s squared over 4 plus s squared over 4, that's s squared over 2, u squared over 2. I cancel out the, simplify the other factor and I get 2 e squared, just the charge, t squared, s squared plus u squared. Okay, so now the question is, so any questions about this still? Okay, so now let's do it the simple way, right? Or let's look at the high energy limit and do it the simple way. In terms of the Mandelstam variables, if we are interested in these lectures, is the high energy limit. So we're interested in. So first of all, the Mandelstam variables when the masses are 0. Generally, there are some particle masses here on the right-hand side, but when the masses are 0, the Mandelstam variables sum up to 0. This is a elementary check which I'll let you make. So when when one talks about the high energy limit, one means the limit where S is approximately minus U. Note that from this you can see that some of these have to be negative. So S is positive, that's the center of mass energy. T and U are always negative. So S is large, S goes to infinity, that's high energy. And of course, we want to look at the high energy limit in such a way that there's some other scale that does not go to infinity. So we don't want to take the limit where all 3 of them go to infinity at the same time. By the high energy limit, we mean the limit where S becomes infinity and T is basically fixed. So T stays about the same. And so and remember T is the square root of the momentum in the propagator. This is a T-channel scattering. So the high energy limit means S approximately minus U and much, much bigger than absolute value of T. T is negative, so absolute, well, yeah. This is where I write the absolute value. Good. So let's look at what happens to this in the high energy limit. So in the high energy limit, S squared becomes the same as U squared. So in the high energy limit, I get 4 E squared, S squared over T squared. Good. Now let me look at my iconal vertex here. Let's do the same thing using an iconal vertex. Here I have P1 and here I have P2. Okay. I have a propagator 1 over T in the amplitude. My iconal vertex for the upper limit is P1 mu. So I have a mu and so the mu is the index here. So the propagator, the propagator, gluon propagator, let me use the same G mu prime. This over T. And then, so there's an I here. I'm not sure about the I's. And then let me write the spin. So there's a spin, and because the iconal vertex conserves the spin, I can just directly write that there's a spin here. Here there's some S prime and an S prime. Okay, for the other. And then from the lower, then the lower vertex is 2 P2 mu prime, like this. And that's it. And that's the amplitude. So looking at, I get P1 dot P2, which is S divided by 2. So my amplitude is directly 2S over T, right? P mu. P. Let me write this again, because this was partially erased. P mu. Right? There's no need to sum over spins, and because so no need to average somehow. The averaging and summing over spins is trivial here, because because now the iconal vertex does not depend on spin, right? So averaging over incoming spins is the same as just taking a fixed incoming spin, no sum needed. And summing over outgoing spins is trivial, because the outgoing spin for each particle is the same as the incoming spin. Right? So there's no additional factor from the spin. Yeah. That's somehow what we mean by high energy. So I think if you start here. So first of all, S is the collision energy. So the high energy limit is S going to infinity. And we don't want to, I mean, it doesn't make sense, I mean, it's not a physically, it doesn't make sense to somehow take all of these variables to infinity. So we define that high energy limit is S going to infinity and T fixed. And then from this it follows that S is minus U, approximately. Okay. Good. So here's our amplitude. And then the amplitude squared summed over spins and whatever is 4S squared over T squared, which is the same result that we got here. So all this trouble, we spent 55 minutes calculating, getting all the vertices right, but somehow if we manage to somehow, if you use the iconal vertex, we get the high energy limit basically for free. We can do it in 5 minutes. So that's somehow this was kind of meant to, there's a price you pay, because doing this kind of approximation, you have to, always there's this worry that, am I doing the right thing? Am I doing an approximation which makes sense? Am I doing something, it's always a bit shaky. But if you're confident that this is the thing that you're supposed to be doing, you really save yourself a lot of trouble using the iconal vertex. It really simplifies your life when you are looking at this specific kinematical limit. Of course, if you want the full thing, you have to do the full calculation, and it's a lot more work. Yes? Let's do exercise 2, and then we'll come back to that. Okay. But I suggest, should we take a break? Let's take a break, then continue working on exercise 2, which is it's a lot simpler. Exercise 2 is the same calculation with lot less algebra. So take a break, have a coffee, come back here, work it out, and then we'll discuss it like at past or something. Okay, so in the interest of time, I think we should go through this. Any volunteers to do the exercise 2 on the blackboard? Come in, yeah. It is simpler than the previous one.
Okay. 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 So I times the amplitude is equal to U bar of K1 times IE u of p1. Then is the propagator, which is, oh no, this is, okay, it doesn't matter. This is minus I over t. And then we have u bar of k2, i.e. U of p2. Is this correct? I think it is. Okay, then from here we can see that m is e squared over t, u bar of k1, u of p1, u bar of k2, u of p2. And so now we can immediately write that is equal to e squared over 4t trace p1 k1 trace p2 k2. Sorry? Oh, no. Oh yeah, t should be squared in. Yeah, sorry. Yes. Okay, and yes, e to the fourth. And now we have e to the fourth, 4t squared. This is now 4 times p1 k1. And this is 4 times p2 times k2. And now this is 4 e to the 4 over t squared. And now we can write this as minus t over 2. Am I right?
I think.
Yes. And this is also minus t over 2. And now we can cancel this, and it's e to the 4.
Sounds good.
Is that correct?
I think so. I don't remember the answer by heart, but I don't see anything wrong.
Okay.
Good.
Okay.
So what's the, yes. So what's the high energy limit? Have you thought about that? So what's the high energy limit if you compare to this? So let's write it next to here. So for scalar, the cross section d sigma over dt would go like the same 16 pi squared s squared times we have e to the 4 over yes,
over nothing.
E to the 4, yes.
Energy.
So how do these compare in the high energy limit?
So in high energy limit we get that there is no cross section.
Yes, the cross section goes to
0. Yes.
Goes to 0. Yes.
Yes.
And so this is very different, right?
Yes.
And often, for example, if I make a detour, let's say you often see people, for example, deriving hydrodynamics from kinetic theory or calculating transport coefficient in kinetic theory. People often use constant cross sections, which corresponds to scalar exchange. So somehow the physics of quarks and gluons, when you're exchanging gluons, the cross-section energy dependence of the cross-section is very different from something where you have a cross-section that is going to 0, that is scalar exchange. So that somehow matters a lot. Okay, so the next question: what if you exchange a graviton? What would you expect the cross-section to look like? I mean, the high energy limit of the cross-section.
So,
as a function of S and T. Any guesses from the audience? There was a guess 0, but I can tell you no, not 0. Other guesses from the audience? if you exchange a graviton, how does the, as a functional form, so here you see that the cross section for spin 1 exchange, the s squared cancels, so this goes like 1 over t squared. This goes like 1 over s squared. Now, note the dimensions. Now you can do a little bit of dimensional analysis. Sigma has dimensions of area,
Okay.
right? And so 1 over gv squared.
Yes.
T has dimensions of gv squared.
Yes.
So d sigma over dt has to have dimensions of 1 over gv to the 4th.
Yes.
Right? So here the s squared in front of my equation always gives that dimension. So what remains here is a dimensionless scattering amplitude. So in the usual relativistic normalization in field theory, 2 to 2 scattering amplitude is dimensionless, right? Spin 1 exchange, it's a s squared over t squared, that's dimensionless. Here you have just a constant, that's dimensionless. So for graviton exchange, so for graviton exchange, of course there's a little bit something that affects the dimensions, but that's maybe not the most crucial point. So what is it that is different between a scalar particle and graviton and a photon?
I mean, we have exchange of something which is tensor of rank 2, am I right?
Tensor, yes. So which
Yes.
means that it has a different spin, right?
Yes, spin 2.
Yeah, spin 2.
Okay, yes.
So any guesses? This is spin 1. This is spin 0. This is spin 2.
1 over t to the 4th.
Okay.
I mean, this isn't guess.
So 1 over t to the 4th dimensionful. Well, first of all, dimensionfully, it cannot be 1 over t to the 4th.
Okay, oh yes, okay. S squared over 1 times
Okay.
t over 4. T on 4th.
So why would it be 1 over t to the 4th? So remember here there's a t squared. Here there's a, well, here you had a t squared and a t squared, right? So you were calculating this diagram. There was always a 1 over t squared from the propagator, right?
Okay.
In the spin 1 exchange, from the vertices, you got an s squared, right? In the scalar case, the vertex also give you a t squared that cancels this. So what happens in the scalar case is that kind of, because the propagator here doesn't carry any Lorentz indices. The propagator is just 1 over t squared. In some sense, there's no way the momentum here can talk to the momentum here. The vertices cannot give you, these vertices cannot give you anything. I mean, S would be a dot product between these two momenta. And the scalar exchange, you cannot have a dot product between these two momenta because there is no Lorentz index in the propagator, right?
Yes.
So therefore, the only thing you can get is the t which you get from these two momenta. So this vertex doesn't talk to this vertex.
Yeah, yeah.
So this is why you get t squared. So you can get some polynomials. So from the numerator, you get some dot products. You get some polynomials.
Yes.
But there's no way to get a 1 over t, another negative power of t, because the negative powers of t always come from the propagators, right?
Well, in principle, the propagator may be some weird gauge where there is GPU minus AU over k squared.
Yeah, so let's say in a covariant gauge where you don't have a, where the propagator is just, I can tell you that the graviton, you can write the graviton propagator also in a way where it's just 1 over k squared, and then something in the numerator maybe, depending on the gauge. Okay, so I will just say that I tell you that there's no way to get a 1 over t to the 4th because
Okay.
the propagator will always give you a t squared. So how about this? What's wrong now?
Dimension.
Dimensions, yes. So okay, so the gravity. What's the coupling constant of gravity?
G.
G. What are the dimensions of, so G Newton, what are the dimensions of G?
I mean, you like a constant.
Yeah, the gravitational constant. Newton's constant G. How is it? GV to what power?
GV2. Okay.
Yeah. Is there? Let's check that in a quick way. This is just non-relativistic physics. Newton's law says that potential is G Newton is proportional to G Newton times mass of A, mass of B over R, right?
Yes. Yes.
So this is GV, this is GV, this is GV.
Yeah.
1 over R is GV,
Yeah.
so this has to be 1 over GeV squared.
Yes.
Okay. So how many? Okay, so this is the amplitude, because so G Newton is really, so somehow the coupling constant, if this is a graviton exchange, the coupling constant here has to be, coupling constant is square root of G Newton, right? Because it's exchanging a graviton. These two couplings together give you Newton's constant. No, now I'm somehow completely cheating you. No, it's it's the potential. I mean, let's see. Now I have to think. Yes, I know that this is a. Yes, the G Newton is, yes. So the G Newton is the potential. So the one vertex gives you a square root of G Newton. And the graviton exchange this diagram altogether, the amplitude gives you a G Newton. So the cross section is a G Newton squared.
Maybe it's less than 4.
Huh?
Maybe it's less than 4 then.
Well, but aren't how do the dimensions work now? We didn't really discuss the S power of S yet, but how are the dimensions? If G Newton is 1 over GV to the 4th, G Newton square is 1 over GV squared. So G Newton squared is 1 over GV to the, how many?
4.
4. And d sigma over dt is 1 over GV to the 4. So remember, I was confused a little bit also that, so S is, yeah, so S is GV squared, right? Yeah. But anyway, S squared over T squared is dimensionless. Right? So you see a systematic spin 0 exchange, S to the minus 2, spin 1 exchange, S to the 0, spin 2 exchange, S squared. Dimensions match. You have the same propagator, 1 over T squared, gives you 1 over T squared everywhere. The coupling, when you take into account the coupling constant, the dimensions match. So this is the dimensions are right. So kind of you would write this as, this would somehow be 1 over S squared G Newton squared over T squared. So this S squared is this S squared, and then and this is S to the 4th, like this. Right? So this would be the dimensionless amplitude, and this is the 1 over S squared in front, right? So this is a very general statement. So somehow the high energy behavior of a cross section is depends on the spin of the particle that is being exchanged. If you have a spin 0 particle, there's no way these two momenta do not talk to each other through the propagator, because the propagator doesn't have a Lorentz index. If it's a spin 1 exchange, then we get the iconal vertex, which is proportional to the momentum here. Then the propagator carries a g mu nu, which allows this momentum here to talk to this momentum here, and that gives you a S in the amplitude, S squared in the conjugate amplitude. So then, presumably a graviton vertex would actually, the iconal vertex for a graviton would have two momenta here. It would be somehow like something like P mu P nu, where P is the momentum of this guy. And then the graviton propagator would have 4 Lorentz indices, which allow 2 momenta here to give a dot product with the 2 momenta here, which give you a very large S. So from this you can also of course see that when you build a future galactic collider that does proton-proton collisions at the Planck scale energy, we don't need to worry about QCD anymore. It's just gravity, right? Because when we go to S, of course this is very small at present day energies because somehow the Newton's constant is Planck mass, Planck energy squared. So this is a very small number, but it has the dimensions that mean that you compensate it with a large energy. So when we go to Planck mass colliders, Planck energy scale colliders, this LS will be the same as this, compensate for this Gn, and the cross section will be, gravity will be the thing that dominates scattering. So this is why at really high energy you need quantum gravity, right? Because yes, that's kind of a gravity system of units where basically, Gn is equal to 1 is basically, the black hole, the mass of a black, so I think the radius of a black hole is proportional to, the Schwarzschild radius of a black hole is proportional to its mass. And the constant of proportionality is the gravity constant. So, so I think in terms, my version of that is that by setting G Newton to 1, you are measuring everything you are defining a standard black hole, a standard black hole whose radius is equal to its mass, and then you are measuring all masses as multiples of the standard black hole mass, and all distances as multiples of the standard black hole Schwarzschild radius. But it's not a very natural system for particle physics. Yeah. There's also a unit system where the fine structure, electromagnetic fine structure constant is 1, alpha electromagnetic, which for us is 1 over 137. You can also use a system of units where it's 1. But then the speed of light is 137 instead of 1. So depending on the circumstance. Okay, this is what happens if you exchange a graviton. If it's a spin 2, you get from this vertex you get two momenta instead of 1 diagonal vertex. From this one you get 2 momenta instead of 1, and the cross section grows a lot. Now, as a final, thank you. I think you can rest at ease. As a final comment, let me make a connection to what the kind of diagrams that Leif drew this morning. So Leif drew something like this. So there was he had a Pomeroy exchange, right? So there was gluon, and then there were these kind of things. I don't know if Leif said that because I wasn't here last week. But here, kind of the way one always, something that people just draw but they never tell you, I don't know if Leif did because I wasn't here, but often people do not, is that when you draw this kind of diagrams, there's a vertical axis in this diagram. There's a vertical axis which is rapidity, y. Which means that there's always up here there are guys with a large p plus component, they are high in rapidity. And in the lower part of the diagram, there are some other particles with a large k minus, right? And so what happens in this scattering process is that some of this minus momentum has to propagate throughout this diagram up here, because here you're gonna, some of this k minus is gonna end up here, some of this p plus is going to end up down here. So they somehow have to go through this diagram. But often, very often in this kind of, looks like a BFK ladder diagram. Very often here, it's always kind of just these iconal vertices in here. So that there's a large p plus here, only a small part of that p plus goes down here, most of it goes down here, most of it goes here. And so it matters a lot kind of what is the what are the spins of the particles that are being exchanged here. In lowest order, in perturbative QCD, at lowest order, the spin is 1. We are exchanging gluon, so that tells us something about how cross-sections evolve. Leif said that, okay, he had a cross-section that goes to some s to the power of 1.18 or something like that. So that kind of looks like, a little bit like there's a particle with spin a little bit larger than 1, right? So in some sense, this reggeon or pomeron or whatever is being exchanged here, it has a specific, I mean, people always use this Donaghy-Landhopp type parameterizations where there's some power of S. And one can think of this power of S as some kind of a spin. It's not really a spin because it's not an integer, but it's something a little bit like spin. Good. But I think this is enough for today now for me. We move to the student seminars.